Hi, Miss Marion here. We are going to be doing lesson 3 and 4 today. So you do need to go back to page 186. We're going to read the I-can statements for lesson 3 so I can find the output of a function when I know the input. And I can name the independent and dependent variables for a given function and represent the function with an equation. So go ahead and write yourself a sentence, give yourself a number. So 1, I don't remember. 2, I kind of remember. 3, I remember. And then 4, I can teach it to my friend. Here is lesson 4 I-can statements on page 187, okay? And so I can use a graph of a function to find the output for a given input and to find the inputs for a given output. And then I can identify graphs that do and do not represent functions. Again, go ahead and write yourself a sentence on how you feel about that. Give yourself a number. So 1, I don't remember. 2, I kind of remember. 3, I do remember. And then 4, I can teach it to my friend. So here is the learning goals. So this is what you should be able to do for lesson 3. After this lesson, you'll be able to calculate the output of a function for a given input using an equation in 2 variables and interpret orally the output of the context. You'll be able to create an equation that represents a function rule and be able to determine orally and in writing the independent and dependent variables of a function and be able to explain it orally. Here is the lesson 4 learning goals. So again, we're doing 2 lessons for today. You'll be able to determine whether a graph represents a function and explain the reasoning on it. We'll be able to identify the graph of an equation that represents a function and also be able to explain it. And then also be able to interpret both in oral and in writing the points on a graph, including a graph of a function and the graph that does not represent a function. So these are all the things that we're going to be learning today. So let's go ahead and let's open up our workbook to page 23. You should have kind of this picture here. It says fill in the table of the input-output pairs for the given rule. Write an algebraic expression for the rule in the box in the diagram. So we have our diagram, we have a side length, and then we're looking for the area, the side length of a square, looking for the area of a square. And so go ahead and fill in this table. So go ahead and pause, fill in this table, and then come back to me. All right, let's go ahead and let's fill in the table. So our input is 8. That is one side of a square. So let's kind of remember what this actually means. So if I did had a square and remember all sides of a square are all the same. But then if we were trying to find the area of the square, it's going to be our side times our side, right? So if my input is 8, so we're going to have 8 times 8. What is that? 64. Next, we're going to be 2.2. So we're going to do 2.2 times 2.2. What is that? 4.84. Next is we have 12 and 1/4 multiplied by 12 and 1/4. That is 150 and 1/16. That can also be, hold on a second, 0.0625. I like to keep it in fraction form because we're given a fraction form. I like to keep it in fraction form. And then think about it, if we put in S, what would be my answer? Well, what we're doing is we're taking S and we're multiplying by S. That is also known as S squared. So now since we kind of looked at this kind of stuff where we have the side length is what our input is, and then our area is our output, we can also think of it as our independent variables and our dependent variables. Remember that our independent variables are all of our x values, right? So these are our x values, like if we were doing a table, and then our dependent variable are also our y values, right? So our input is our x, output is our y, so input is our independent. So think about science, right? We were doing independent, dependent, and then this is our dependent. So we can say that the area of a square is dependent on the side length. So whatever your side length will kind of change, your area is going to change, right? So we've kind of done this before. We've done this. We've been doing it in science. We've been doing it with our graphs, all that kind of stuff. So our independent variable is our x values, dependent is our y values, and this is a function. So we kind of have like something depends on another. We've been doing this for a while. So hopefully kind of jog your memory on that. All right, let's go ahead and turn to page 24 to 25. And so we have all of these different function pictures, right? And what we're going to do is we're going to match each of the descriptions with a diagram. So we have A, B, C, and D. There is a table that you can go ahead and fill in if you need to, or you can just write next to it which ones they are. So up to you on that kind of thing. And so I'm going to go ahead and have you go ahead and match these. So pause it, match it, and then come back to me. All right, let's kind of go through this. So we have the circumference C of a circle of a radius R. So which one of these pictures down here is going to be this one up here? And if we look at it, if we think about circumference, remember circumference is 2 times pi times radius. So which one is that? So the letter D is going to be this one up here. Let's look at B. The distance in miles D that you would travel in T hours if you drive 60 miles per hour. So remember, our distance is our rate times time. They say that our rate is 60, our time is T. So which one is the little b is going to be? It's going to be big B. Okay. And then let's look at little c. It says the output when you triple the input and subtract 4. So which one of the function pictures is that one? Well, we have it as C. And then D, the volume of a cube, V, is given as length of S. So remember, if we have a cube, and remember that the cubes, the sides are all the same. And the volume is going to be our length times width times height. So which one is that going to be? Oh, that's going to go letter A. So these are all the pictures that go along with number 1. All right, so here are all the pictures that match with all the numbers. We kind of went through this, but I wanted to make sure the pictures go along with it so we can make sure that that actually is what it is. So here are our answers. And then we're going to move on to number 2. So number 2, it says write an equation for each description that expresses the output as the function of the input. So go ahead and try that. So pause and try it, and then come back to me. All right, let's go ahead and let's look at this one here. So letter A. So what are we looking for? So what we are looking for our circumference. So we're going to say C equals our 2 times pi times our radius. So this is going to be our equation for this function picture. Let's look at letter B. So over here, okay? So it says distance miles D. So we have it as, so we're looking for our D, right? And we're trying to travel 16 miles per hour with our time of T. So what would be our equation? This one would be D. Let's actually try something else. Hold on just a second. Let's do D equals 60 times T. Let's look at letter C. Okay, down here, the output of the triple of the input, subtract 4. How would we write that as an equation for our function picture? So we're looking for the y, and it's going to be 3x minus 4. And then let's look at letter D. Last one, right? It's the volume of a cube. How do we write that as an equation? We're going to say our volume equals s squared. So these are all the answers for number 2. So now that we have our equations, I don't have our equations typed in here, but now that we have our equations, we have our function, things that go along with it. Number 3, find the output when the input is 5 for each of the equations. So for all A, B, C, and D, you're going to go ahead and put 5 in and then see what the answer will be. So go ahead and pause that. And then again, you can be doing the table. You can fill in the table along with this. I like to kind of do it all together to kind of make it sense. But you can fill in the table if you need to. But again, put in your input is 5 and then figure out your output. So go ahead and pause and then come back to me. All right, so let's go ahead and let's go through this. So letter A, right? We're looking at letter A. And remember, our equation was C equals 2 times pi times our radius. And then we're saying that our radius is going to be 5. So we're putting 5 into our function, our equation, our function picture. And we're going to say 2 times pi times 5. We can do it as 2 different ways. We can do it as 2 times 5 is 10, and then pi. This is the way that mathematicians like to write it. You can also do the 10 times your pi button, and you're going to get 31.4159, keep on going. And also you can do it as 10 times 3.14, and then you're going to get 31.4. So any of these will be the answer for letter A. Let's go ahead and do letter B. So again, our T is going to be 5. Our equation that we wrote was D equals 60 times T. So let's go ahead and do that. We're going to do 60 times 5 times T. So what is 60 times 5? That is 300. So our answer is going to be 300T. So our input is 5. Our output is 300T. So our independent is 5. Our dependent is 300T. Okay. Let's look at C. So C, our equation was y equals 3x minus 4. Again, our input is going to be 5. So we're going to do 3 times 5 minus 4 due to order of operations. So we're going to do 3 times 5. That is 15 minus 4. That is 11. So our input is 5. Our output is 11. And then let's do our last one. Our equation was v equals s cubed. Again, our input is 5. So then our output, so we're going to do 5 cubed. So our output is 5 cubed. How do we put this in the calculator? So we can either do 5 times 5 times 5, or we can also do it as in our calculator. I'm going to put this in a different color. We can do 5 and then this little carrot. We call it carrot top kind of thing. Looks like housetop, rooftop. 3. And then our answer is going to do 125. Okay, so then our input for T, our input is 5, our output is 125. So on number 4, we're going to go ahead and label our independent variable and our dependent variable for all of the different things. So remember what independent and dependent, remember, we've been doing that forever, okay? So go ahead and pause this and then come back to me. All right, let's look at A, right? Trying to figure out independent and dependent. So we're going to say our independent variable is going to be R. Our dependent variable is going to be C. Let's look at B. So our independent, what do we put into the function, is T. Our dependent is D. What is our output? Independent for C, letter C, is going to be X. Our dependent is going to be Y. And then letter D, our independent is S. Our dependent is V. So looking at all of these, on page 27, we have an independent variable definition. So remember, independent variable is a variable represent the input of the function. We also know our input as our X value. So go ahead and do a definition on page 27 for independent variable. And then go ahead and put it in your terms. You can write down what I have, put it in your terms, but go ahead and write it down in this area. Also on page 27, it's dependent variable. So a variable representing the output, or we also know as the Y, is considered our output of the function, is our dependent. So go ahead and define dependent variable on page 27. You can either write it down how it is right now or put it in your own terms, but go ahead and do a definition for, so you should have independent and dependent definitions on page 27. All right, let's go ahead and go into lesson 4. Let's turn to page 31. We're going to look at this graph, and it says, what might the graph represent? So go ahead and pause and answer that question, and then come back to us, and we'll talk about it. All right, so what could this represent? So look at the independent variable, our X value, and it's going up by months. And then we have our inches, and it's our H, which is our dependent variable, and it starts probably around 13, and it actually increases. So this could be looking at plant values or trees that are growing or are snowpack. You're starting at a certain area and you're talking about snowpack. So all of these can actually represent a lot of different things. So this is getting our minds going about graphs and what they actually represent. All right, on page 32, we are going to be looking at these graphs. So the graphs of three functions are shown. Number one, match each of the equations to one of the graphs. So we have A, D equals 60, where D is the distance in miles that you would travel in T hours if you drove 60 miles per hour, just 60 miles per hour. B is Q equals 50 minus 0.4 D, where Q is the number of quarters, D is the number of dimes in a pile. And then C, where it's A equals pi radius squared. Sorry, that looks a little bit different than your book, and it's because I don't have the capability of typing that, how it looks in the book, but okay. Where A is the area in square meters of a circle with a radius are in centimeters. So go ahead and match the pictures to the information that's given to us. So go ahead and pause and then come back to me. All right, number one, what graph should go with number one? That is B as in boy. So the B is number one, and it's because you're always just going on a constant rate. It's going to go ahead and change itself. Number two, this one, it should be C. And the reason why is because this is the only one that has a negative slope, okay? So it's going to go ahead and go down the hill. And then the last one, the C, so letter C, should be graph A. And so these are the ones that match up with it. Number two, label each of the axes with the independent and dependent variables and the quantities they represent. So go ahead and label your graphs. So pause, label your graphs, and then come back to me. All right, let's go ahead and let's label these. So let's start with letter A, as far as the D equals 60T, that was graph B. And so remember that our independent is our x-axis, our dependent is our y. So D equals 60T. The D, or the distance, is going to depend on the time. So we're going to have it as time on the bottom. And then we're going to have it as distance on the y. Let's go ahead and look at tiny little letter B. Q equals 50 minus 0.4 D. So Q is going to depend on D. Q was the number of quarters, and D was the number of dimes. And then letter A, so letter A is A equals pi radius squared. So the area is going to depend on the radius. And again, the y-axis is the dependent, x-axis is the independent. All right, number three, for each function, what is the output when the input is 1? What does this tell you about the situation? Label the corresponding point on the graph. So again, go ahead and pause, go ahead and do that, and then come back to me. All right, so let's go ahead and do that. We're going to start with this one first, letter A, right? And so we're going to go ahead, and they're saying that our input, so our T is going to equal 1. So let's go ahead and let's do that. We're going to say D equals 60 times T, or sorry, 60 times 1. And so we're going to go ahead and do 60 times 1. What is that? Oh, that's 60. So our point that we're looking at is 1, 60. And and that was graph B, okay? And where is that? So we're going to have 1 and 60. It's kind of about here on the graph. Let's go ahead and look at number 2. Let's look at little b down here, okay? And so they're saying that our independent, our x-axis, is 1. And so what was our x-axis on this? Well, that was our dimes. So that means our D is going to equal 1, okay? So we're going to go ahead and put that into our equation. So we have it as Q equals 50 minus 0.4 times 1. And so let's grab our calculator. Let's go 0.4 times 1 is 0.4. So we're going to say our Q equals 50 minus 0.4. So what is our Q? So our Q is going to end up being 4.96. So our point that we want to go ahead and graph is 1,49.6. And let's go ahead and put that on our graph. So we have 1 and 49.96. That's kind of this point here. And so that is that question. And let's go ahead and do our last one. So remember, on our last one, we have it as the radius is our independent. So we're going to say our radius equals 1. We're going to go ahead and put it into our equation. So we're going to have a equals pi times 1 squared. And so what is pi times 1 squared? Well, that's like 1 pi. Okay. And so we can either do it as 3.14 or we can do it as 1 pi. A lot of mathematicians like to do it as 1 pi. And so that point is going to be 1, 1 pi on the graph itself. Number 4, it says find 2 more input-output pairs. What did they tell you about the situation? Label the corresponding points on the graph. So again, pause and then come back to me. All right, as you can see, I went ahead, all the blue points are the different ones that I went ahead and put in. You do not have to do these. This is up to you. So the 4 times pi, you can either do it as 4 pi, or you can actually go ahead and multiply 4 times 3.14, or the pi button and get about a 12.56. So you don't have to do it as 4 pi or 9 pi, but that's how mathematicians like to do it. So this kind of shows how it kind of goes up itself. We have 2 and 120, 3 and 180 on the d equals 60t. So it's showing how the time traveled going along, you're actually going farther. And then also on here is the quarters and dimes. It's kind of showing how those go ahead and relate to each other itself. So this activity, what we're looking at is all the independent and dependent variables. Remember, our independent is our x-axis and our dependent is our y-axis. Just like science at the beginning of the school year, we're actually kind of going over all that stuff. We're actually just applying it to our graphs. All right, let's go ahead and turn to page 35. Let's look at another kind of some graphs and what they actually entail. And so here is number 1. Kieran was running around the track. The graph shows the time t he took to run various distance d. The table shows his time in seconds after every 3 minutes. And so go ahead and answer the questions A through E. So A, how long did it take Kieran to run 6 meters? B, how far had he gone after 6 seconds? Estimate when he had run 19.5 meters. Estimate how far he ran in 4 seconds. And then E, is Kieran's time a function of distance he has run? So go ahead and pause and answer all those questions and then come back to me. All right, let's go ahead and answer the question. So how long did it take Kieran to run 6 meters? So if we kind of look at it as far as our table, how long did it take him to go ahead and run? Well, it took 2 seconds. Number 2, how far had he gone after 6 seconds? So let's go ahead and kind of look at that. So we have 6 seconds on our table. How far did it take? How far did he run? He ran 18 meters. C, estimate when he had run 19.5 meters. And so if we look at our table, so we're looking at 19.5 meters. Here's 18 and 21. It's going to be more closer to 18. So it's 6 and then 6.9. So again, we're going to go ahead and estimate this. So how long would it kind of take to go ahead and do it? Well, I think it's probably going to be somewhere between those two. So about 6.5 seconds. And then D, estimate how far he ran in 4 seconds. So again, let's go ahead and look back down at our table. So we're looking at 4 seconds. So 4 seconds is about between these two. So we have 12 and 15, between 12 and 15 itself. And so, how would it be as far as that 4 seconds, as far as how far would he have ran? I'm thinking probably around about 12.8, 12.75, so 12.8 meters. So looking at all of this, so we're asking, is Kieran's time a function of the distance he has run? And so Kieran's time is a function of the distance he has traveled. And it's kind of, if by reading the graph, we can see which one would be our independent and then which one would be our dependent variable. So if we go ahead and read this graph right here, see how it has the distance is here. So remember that the x-axis is our independent and our y-axis is our dependent. Okay, so this situation that we have is that the time is dependent on the distance. So it's a little bit different than what we're used to. We're used to seeing it the other way, but because we're looking on a graph and it actually shows us which one is which, this one is time is dependent on the distance. All right, let's go ahead and turn the page and let's look at a picture about Priya. Priya is running once around the track. The graph shows her time given how far she is from the starting point. So we're going to answer all the ones. So A, what was her farthest distance from her starting point? B, estimate how long it took her to run around the track. C, estimate when she was 100 meters from her starting point. D, estimate how far she was from the starting line after 60 seconds. And E, is Priya's time a function of her distance from her starting point? So go ahead and pause, answer those questions, and then come back to me. All right, let's go ahead and go through this. What was the farthest point that she actually ran? So this is where her starting point is. So she's running. How far did she go? She went about 200 meters. So B, estimate how long it took her to go run 75 meters. So if we look at our graph, estimate how long it took her to run around the track. So remember that she starts at the starting point, she goes all the way up to 200 meters, and then she kind of comes back. So how long did it take her? Oh, probably about 75 seconds. All right, C, estimate when she was 100 meters from her starting point. And so as far as her 100 meters, so let's go ahead and look at the graph. So 100 meters, oh, well, that's probably here. It's probably about 18 seconds. And then notice how there is another one. So 100 meters, here's 18, and then also here's one up here. Oh, that's probably about 55 seconds. D, estimate how far she was from the starting line after 60 seconds. Okay, so let's go ahead and look at that. So we're looking at 60 seconds. So 60 seconds is probably in between. So let's go back to our graphs. We have 60 seconds is this point, right? Let's go ahead and go across. Well, there's only one point that goes with that. And what is that one point? Well, that's going to be 75 meters. So the last question is Priya's time a function of her distance from her starting point? So remember, we were talking about functions the other day, and we were doing those function diagrams. And we were looking at it, and we're like, okay, function has to have like one input for every one output. One input, one output kind of thing. And so is this the time a function of her distance? No. The time is not determined by the distance from the starting line. And so, no, it's not. Time is not determined by the distance from the starting line itself. So that answer is no. So today we've been kind of looking at graphs and figuring out the functions and looking and seeing what information we can go ahead and get. We've been talking about independent and dependent variables. So remember, the independent is our x y-axis, right? And then which is usually what we put into, so it's also our input, and then dependent is our output, or the y-axis. And so we've been talking about these kind of things, and so how does those relationships kind of go along with each other? So again, input, outputs, everything that we've been going together. So we did lesson 3 and 4 for today. So go ahead and go back to page 186. This is icons for lesson 3. So I can use a graph of a function to find the output for a given input and to find the inputs for a given output. And I can identify graphs that do and do not represent functions. So that was lesson 3. So write yourself a sentence, give yourself a number. 1, I'm still confused. 2, I kind of got it. 3, I did get it. And then 4, I can teach it to my friend. And then go ahead and also do the learning targets for lesson 4 as far as those I can statements also. So you should have 2 sentences and 2 numbers for today on page 186 and 187. And remember, so we're doing inputs and outputs. Again, we are doing 2 practice problems for homework. Okay, so keep that in mind. And so I hope you have a good day. Thanks.